Hi, I'm Munawar Hafiz, Chief Technologist of Open As you can see from my backdrop, I'm in a hotel room right now. I'm traveling and I'm attending the Open Source Summit North America in Seattle at this point. In between the conference talks, I'm taking some time off to record this video. My talk explores the static analysis tool landscape for Go language, specifically what kinds of bugs they find, what kinds of bugs they miss, and how Open Refactory's Intelligent Code Repair, or ICR, is bridging the security tool gap that is left by the other tools. We are all aware of the challenges of keeping applications secure. The average cost of a security failure now is about $10 million. Yet, over 150 security vulnerabilities are reported every week in the National Vulnerability Database. Current static analysis and dynamic analysis tools fall short of detecting these bugs in time so that these breaches can be avoided. In fact, research data has shown that existing static analysis tools detect only about 14% of all the bugs detected. The remaining 86% of the bugs are detected by pure luck. This is pretty staggering. At the same time, the static analysis tools operate at about 50 to 90% false positive rate. Imagine a 90% false positive rate. 10 bugs that is reported by a static analysis tool, out of that, 9 of them are not a bug at all. And somebody in your team needs to painstakingly go through each of the bugs to triage and identify what are the bugs that your team needs to fix in the first place. Finally, the static analysis tools fall short of fixing the bugs. They only detect. Bug fixing remains a manual process, and oftentimes this is very error-prone. There has been several incidents where a bug fix was not only able to address the security problem, and in other cases, it has also introduced some other bugs. The most daring example in this space is that of the log4 shell vulnerability. When the log4 shell vulnerability was reported, there were 4 different fixes that were released in a span of 4 days. And each of the earlier ones were not able to fully address the problem. This, unfortunately, is very common in the industry. And because of this, teams miss deadlines, administrations have budget overruns, and companies have recurring security breaches. Open Refactory's Intelligent Code Repair, or ICR, addresses these challenges head-on. ICR finds bugs that other tools miss. It does that with dramatically low false positives, and it is the first tool in this space that can automatically synthesize fixes for about half of the bugs that has been detected. Because of this, developers get their life back, and companies can deliver high-quality software on time and within budget. ICR is available for Java, Python, and Go programmers. An instance of ICR harbors many different fixers. Consider ICR as a band of superheroes, where each fixer is a separate superhero with its own separate power. It can detect and occasionally fix a different kind of security, reliability, or a compliance bug. ICR fixers are built upon 3 key technologies. We use deep static analysis based on path analysis to detect the bugs with high accuracy. We use machine learning and also generative AI for different cases to improve the results. Specifically, generative AI is good for summarization and generation. We use the summarization capability to understand the programming context better, to reduce the false positives, and we also use the generation capability to further improve upon the bug fix generation capability of ICR. Finally, ICR is based on code refactoring technologies. I've been part of the code rewriting community for over 20 years, and I've built code rewriting tools in over 10 different languages. Open Refactory brings together that expertise in code rewriting to deliver the fixes for you. I've already mentioned that the results from ICR is highly precise. On benchmark, we have shown as low as 3% false positives in ICR results, and typical bug detection tools operate at greater than 80% false positive rate. Therefore, ICR allows a development team to operate at premium release velocity without compromising the quality. It improves the productivity of the developers by about 11% or more. And the developers are now freed from the mundane task of bug fixing and can focus on more creative work of feature creation. Now I'll share a video made by Charlie Bedard, who is our Chief Operating Officer, and he will explain the ways you can use ICR and a basic workflow of using it. ICR is available in Java, Python, and Go, so the video is generic, but it gives you the idea of how to use it.
Now, let me give you a brief overview of how ICR works. ICR is a suite of Docker containers that control access to your code repositories, analyzes your projects, and allows you to review and accept the results. The Navigator is accessed via a web browser, and it authenticates each user and provides a view of the user's repositories. Repositories are accessible through many popular version control systems, such as GitHub, GitLab, and Bitbucket. The analysis engines do the heavy lifting of scanning your projects and detecting the bugs. There is one analysis engine for each language that ICR supports. The reviewer is used to examine the output of the analysis engines. You can examine the bugs that ICR has detected and accept or reject them. If a fix is offered and accepted, the reviewer can also apply those fixes directly to the source code in your project. To analyze your code, you first log into the Navigator. Select the project you wish to analyze. The Navigator then fetches the code from your VCS. You then select the branch that you want to analyze and start the analysis. The Navigator scans the project and presents you with the language options. After selecting the language, the appropriate analysis engine is invoked. When analysis completes, the results are placed into a database for later review. Let's look at that next. To review the results of an analysis, the user connects again to the Navigator. For this step, the analysis engines are not used. Their work is complete. However, we do need to start up a reviewer session to go over the detected issues. With the reviewer connected to the user, they can browse the detected bugs and choose which bugs to accept or reject. Once a bug is accepted, and if there's a synthesized fix for it, ICR can push the fix to a temporary branch for further review by the development team. Using ICR is simple and effective in finding critical security vulnerabilities in your projects. Let's see these same steps from the user's point of view. After logging into ICR, the Navigator presents the user with the repositories available through the chosen VCS. In our example here, we are using GitHub. We scroll through the projects and choose the one we want to analyze. I have chosen an open source Python project named Manim. We first clone the project to pull the source code into ICR. Then we choose the branch that we want to examine. In this example, we'll analyze the main branch. Click on the Analyze button to begin the analysis. ICR detects that this is a Python project and asks us to choose the version of the Python library to be used for this analysis. We do that and continue. Analysis begins. As the analysis proceeds, you can log out of ICR and return later to see the results. Or you can monitor the progress from the Monitor page. Some analyses may take quite a while, but this one is quite quick, so we can see the analysis proceeding. When it completes, we can look at how the reviewer is used to go over the results. With the analysis complete, we return to the Navigator to begin the process of reviewing the results. Again, we scroll down to the Manim project and select its main branch. We now see that the Review button is available to us. Clicking on that brings us to the Analysis Summary page, where we can see the history of all the analyses previously performed on this branch. In this example, we have the analysis that was just completed. Clicking on the Show Results button brings us into the reviewer. At the top of the page, we see a summary of the results. The bugs themselves are presented below that and are prioritized, with the highest severity issues shown first. At the left of the window are some filters. We use the category filter to narrow down the particular class of bugs we want to review. For example, we can look at just the bugs in the improper method call category. There is an issue titled IMC-M-1. It is a medium severity issue. The description gives details about the issue, including links to external sources that describe the importance of the issue. By clicking on Show Diff, we can see the specific issue highlighted in red, with the recommended fix shown in green. If we want to accept the fix, all we need to do is click on the Accept button. In this fashion, you can review all of the identified bugs and choose which ones to act upon. To read more about how to use ICR for your projects, you may want to read our online ICR user guide, or feel free to contact us at info@openrefactory.com.
Now, let us go through a demo of running a few options of static analysis tools on a single application and identifying what kind of bugs are detected by the different static analysis tools. For this, I will be using 3 static analysis tools. One is an open source tool created by Google called Golang. The second is the ubiquitous Sonar Cloud, and the third one is ICR, or Intelligent Code Repair. I'll be running all of these on an application that has been built by Red Hat. It's called Service Provider Integration Operator. The application is not very big. It is about 20,000 lines of Go code as well as others. For this talk, I'll be just concentrating on what these tools are finding in the Go code. There's one other thing. In order to make things interesting, I'm not running the tools on the current version of Service Provider Integration Operator. Instead, I went back in time and identified a version which had 2 critical problems. One, a cross-site scripting, and another one, an open redirect issue that was there and fixed later. I'm going back to a version that has both of these vulnerabilities. So the challenge for the tools is to identify these 2 bugs if possible. That particular vulnerable version of the Service Provider Integration Operator is stored in a separate public repository called Service Provider Vulnerable. I'll be running the tools on that application. First, let's run Golang. Golang is run from command line and is pretty straightforward. You just specify the output directory where you want to store the results and run it. Note, here we are running on the current directory, but you can instead choose any subdirectories on which you can run. You can also pick and choose the set of rules that you want to run. Here, we're running with all the possible rules that are provided by Golang. When we look into the results, we see that Golang does not find anything at all. This is okay in terms of false positives, because at least we do not have to triage through tons of false positives thrown by Golang. However, we are not getting any improvement in terms of security. Specifically, we know that there are 2 critical security problems here. So the fact that Golang does not find anything means that your risk remains unmitigated. Now let's look into Sonar Cloud. We are running Sonar Cloud on the same application. I've already run the application and are now showing the results. Sonar Cloud identifies 33 security bugs, 6 reliability bugs, and 257 maintainability bugs in the code. That's quite a handful. Let's look into each one of them. But before we do that, first filter the Sonar Cloud results so that we concentrate on the results identified in the Go code only. If we do that, now our number of bugs have come down to only 206 issues. But as we see, that we do not find any security issues anymore. We are only finding maintainability related issues. Some of them high severity, some of them medium severity, and some of them low severity. We see that the results reported by Sonar Cloud were of three kinds. They were about duplicated string literals, some of them were about the cyclomatic complexity of some functions being high, and then there are some empty functions. None of them appear to be very serious at all. In fact, we are still searching for a tool that can identify the critical security problems that are lurking in the source code that we are running upon. Now, let's look into ICR. Again, in this case, you are accessing ICR through the web portal. You are selecting the GitHub repositories that you have, and once you're connected with GitHub, you'll see all of your repositories. Here, I've run on the vulnerable service provider application beforehand, and so let me open the application. You see that there are several branches on which we can run separately, but in this case, we ran already on the master branch, and we have the results already available. Once we see the results, we see that ICR only identifies 2 bugs for you. And voila, it has identified both the security issues for you with 0 other unnecessary issues, which means that there is 0 false positives. If we see the output of the first bug, which is the open redirect, we see that ICR provides you a trace of where the taint came into the application and where it was exercised so that the open redirect will happen. In this case, ICR was not able to synthesize a fix. Now, if we look into the cross-site scripting, we see that the trace is longer because the code flows through multiple paths. ICR provides the detailed trace. But what is interesting is ICR was also able to synthesize a fix in this case. The fix was sanitizing the input coming from an untrusted user with a well-known library called Blue Monday. ICR not only included the library calls, but it has also imported the library module. So we have seen that ICR has only identified 2 bugs, both of them that we were looking for in this case, and it was able to synthesize a fix for one of them. Okay, as you see that with the magic of video editing, I have changed my dress and I've come back home from the conference. So let's summarize what we have covered in this talk. I've looked into the problems that current developers face when they're looking for static analysis tool support. I've also done a test drive of multiple static analysis tools on a known application that has been created by a reputable vendor. And I've shown that only ICR, or Intelligent Code Repair, was able to deliver the promises that was made by it in the first few slides. It was able to find the hard to find bugs. It was doing that with no false positives in this case, and it was able to synthesize fixes for one of the high severity cases. Consider using ICR as opposed to another tool that was reporting over 200 issues, but all of them were false positives. If your developer was taking, on average, about 10 minutes to look into each one of the bugs and identify whether that's a true positive or not, then it's going to take him about 2000 minutes in order to triage the bugs. Now you can tell me, Munawar, the problems that were identified were pretty benign and it doesn't take 10 minutes to triage them. Well, in this case it was true, but on another application it may not be. The bottom line was that other tools were not able to find any critical bugs, and they were just instead generating a lot of false positives. And there you have it. If you have any questions, feel free to reach us at info@openrefactory.com. We'd be happy to let you do the test drive yourself and identify the benefits that ICR is providing. Thanks a lot for your time, and I'm looking forward to chatting with you afterwards.